La la la. Still working. All right. So, if you're in my Calculus 2 class in the morning, my apologies. I forgot to turn on the mic this morning. So it's a silent treatment. But here, I turned the mic on, so hooray. Of course, you're here, so what do you care, right? Let me begin with a word of prayer. So, Dearly Father, we thank you for this day. I thank you again for these students. I just ask that you'd guide our steps today, help us to glorify you, what we do. Help us to just take joy in your creation that you have graciously provided for us as a place to live and to understand your laws, Lord. In your name I pray, Lord Jesus. Amen. So I'm doing things a little bit weird this semester because I typically do vectors and then I start talking about one-dimensional motion, and then later I introduce the vector formalism for position. But since I already did what I did last class, let's just finish that discussion, right? So motion in 3D, basically you need to use vectors to describe motion in 3D, right? So the essential idea is you've got some coordinate system, right? And how you set that up, well, that's your business. But, so you have some origin and you can measure distance, right? 2 different directions and then a vertical direction, 3 perpendicular directions, yeah? And then we can talk about 2 different points in space, like, this point and say this point over here. So this could be, say, R at time 1, and this could be R at time 2, right? And so these would be the positions of an object at 2 different times, right? And then we can talk about the displacement, right? A displacement is a change in position. So the displacement would be something like going here like this. This would be the displacement. So change in R, which should be R of T2 minus R of T1. This is the displacement. So displacement, right? Displacement over the time interval T1 to T2, right? So here I'm assuming that T1 is less than T2. An interval of time is also called the duration, all right? So we can talk about the displacement that happened during duration T1 to T2, yeah? And once you have that, then you can start talking about, well, you could talk about average velocity, right? So like average velocity, if you wanted to, average velocity would be the displacement divided by the duration. So here, delta t is T2 minus T1, right? And then you could take the limit as delta t goes to 0, and that would be another way you could describe the instantaneous velocity, right? At, say, time 1. But in here, by default, when we talk about velocity or acceleration, we're not talking about average velocity or average acceleration. We're going to be using calculus, and we're going to be talking about the instantaneous velocity or the instantaneous acceleration, right? It's useful for me just to take a second here and say a little bit more about this picture. See, because there's more that we can see here. So we have, this is the position vector R1, right? This is the position vector R2. Let me call this R1 and R2, if you'll allow me. And what we see here is that R1, right, plus the displacement vector is equal to R2. Can you see that? Some of you are sitting too far to see it, but imagine this is R1. Then we tip the tail, add the displacement vector like that, and that's the same as R2. So this is, we can understand this in terms of tip-to-tail vector addition as well. But this is what the displacement means. It's your starting point, then you displace yourself, and then you get to the ending point. All right, this is displacement. It's a vector in general. Now, notice also that algebra is really nice here because you can also see that like the displacement is r2 minus r1. See that from here? See that as well. Okay, so last time I defined velocity and acceleration and even the jerk for you, right? But there's another thing which is interesting in addition to the displacement, which is the distance traveled, right? So distance traveled, let's talk about that for a minute. So here, you might start, say, at this place at r of t1, right? And then you might travel some kind of crazy path, loop-de-loop, whatever, over to here, right? Your final resting place there being r of t2. All right? The distance traveled, what that means is the length of that red string, right? If you were just to take it and pull it straight, right? In other words, in Calculus 3, if you've had it, it's what we call the arc length of the path, right? How do you calculate the distance traveled for such a curve? So the distance traveled, which is equal to the integral from t1 to t2 of ds dt dt. Now here s is arc length, all right? What is ds dt? And so the arc length would be like the integral from, say, t1 to t of the square root of dx dt squared plus dy dt squared plus dz dt squared dt. So you integrate. But what is that? What's that thing I just wrote down? There's a simpler way to look at this. In other words, s of t is equal to the integral from t1 to t of, this is the velocity. Excuse me, that's not the velocity, it is the magnitude of the velocity. What's the magnitude of the velocity? We have a name for that. So last time I told you velocity was dr dt, right? So that's also going to be equal to v hat. Here v, the magnitude of the velocity, is by definition the speed. The speed is the magnitude of the velocity. I'm making a definition, right? But if you integrate the speed over time, it gives you the arc length. And notice the fundamental theorem of calculus part 1 comes into play here. If you differentiate this with respect to time, what do you get? ds dt is what? d dt of the integral from t1 to t of v dt, which is just v again. Because when we differentiate an integral with the variable bound, we get back the integrand again, right? This is FTC1. You guys have had calculus 1, you know this. So yeah, this is all consistent. You integrate the speed, right? Because the speed is the instantaneous, the instantaneous rate of change of arc length with respect to time. So if you integrate that instantaneous rate of change, the net change theorem says you get the total arc length. So anyway, long story short, takeaway message from all this is the formula for distance traveled is simply this. Integrate from t1 to t2 the speed. Any questions about this? Let me show you an example. If we had position at time t to be, let's say, r cosine omega t, and then let's say mt r sine omega t. So here's the path, a particular path through space, right? You could study this path. And so let's just go ahead, let's calculate the velocity, the speed, and the arc length. Well, actually, let's find the distance traveled from t equals to 0 to t equals to, oh, I don't know, 2 pi over omega. Okay? Here, omega and m are just constants, okay? So what's the velocity? Can you differentiate? We've got what? Minus r omega sine omega t, m, r omega cosine omega t. So there's your velocity. What's the speed? We need to calculate the magnitude of this vector, right? So the speed is the square root of minus r omega sine omega t quantity squared plus m squared plus r omega cosine omega t quantity squared, which is actually really, really nice because cosine squared plus sine squared is what? It's 1, right? So the cosine and sine actually go away, and this is actually the square root of r squared omega squared plus m squared. So this actually is an interesting curve because it has constant speed. Yet its velocity is not constant, right? Its velocity is always changing direction. In fact, the acceleration is non-zero, right? This is actually a helix. It's like twisting around the y-axis is the motion here, if you were to picture it. Something like that is what's going on here. It's constantly drifting over in the y direction at a constant rate of m. Its y velocity, we would say, is m. See, the y velocity is m. Okay. So what? Well, then, the constant speed, what's the distance traveled? Well, the distance traveled, the change in arc length would be integrate from 0 to 2 pi over omega, this number, and how do you integrate a constant? Well, that's, you just pull the constant out and multiply by the length of the integration, right? So the answer here is just 2 pi over omega times the square root of r squared omega squared plus m squared. So the answer isn't particularly interesting, but my point to you is, in this particular one, the speed is so nice that we can actually just straight calculate the distance traveled. Usually, you can't do this. For even the most simple path, when you take the square root of a sum of squares, that's nothing nice in terms of integration usually. So in your homework, I think I've told you can use a numerical integrator to find the distance traveled, right? However, truth in advertising, one of your homework problems is like this. So you actually don't need the numerical integration. I think the problem at the end about Kakashi, I think that requires numerical integration, yeah. Well, what?
What does delta S represent?
The change in arc length, the total change in arc length.
Is there another name for that?
Distance traveled, yeah. So that's all I have to say about three-dimensional motion here for a little while. So what I'm going to do now is I'm going to specialize, all right? So we don't always need vectors, right? Like oftentimes we need vectors, but if we're talking about a problem that's one-dimensional in nature, we can get away with dropping the vectors, all right? So one-dimensional. One-dimensional motion, right? So for example, we could talk about x is the position, dx dt, velocity, d squared, dv dt, velocity v. dv dt would be the acceleration, right? And in the one-dimensional context, we have other things that come into play, right? So what would speed be here in one dimension?
Just velocity.
It's not just velocity. It is the magnitude of the velocity, which, by the way, is the square root of v squared. Now, admittedly, so this is so here's where the notation admittedly has a problem, right? Because we've used the symbol v to denote the magnitude of velocity, right? But in one dimension, we just use v to be the velocity. So you have to understand it in context. I'm sorry, physics is just this way. There are worse things. We use the letter p for about 10 different things in introductory physics, okay? So just understand, in one-dimensional motion, v doesn't mean speed. The speed we don't really have a symbol for. We just call it speed. It is the absolute value of the velocity. All right? So that's something to watch out for, I guess. And the other thing that's cool about one-dimensional motion is we also have graphing. We can graph position versus time in one dimension, right? Like, in one dimension, we can draw pictures like this. T and X, yeah? And we can do things like, maybe the position looks like, I don't know, this. If this is, the position, what's the velocity look like? The velocity is the derivative of the position, right? So it's apparently 0 right here. And it's increasing here. So I guess it does something like this. It's 0, it's decreasing, kind of levels off. Maybe this is the velocity graph. What's the acceleration? Acceleration is derivative of the velocity, right? So what's the graph of that? So remember, acceleration is the change in the velocity with respect to time, right? So wherever the velocity, so this is admittedly ambiguous from my graph, right? I'm just trying to give you the concept, like it's not quite careful enough to be rigorous about where these things go. It's just a heuristic sketch here, right? But when the velocity maxes out, that's where the acceleration is 0. So if there's like right here would be like acceleration 0. And I think that's it. So the velocity is increasing. So, and then the velocity is decreasing, but it kind of mellows out here. So something like that would be the acceleration curve. Let me do another one. This one's easier. It's easier for me if I start with the acceleration curve. So suppose the acceleration curve is this. Suppose you have what's called constant acceleration, and it's negative, all right? So here's my constant acceleration. Again, I'm making a time versus position graph. And there's something kind of funny going on here in the sense that I'm going to call this y. Because we're graphing velocity, position, and acceleration all on the same graph, right? So in terms of like dimensional analysis, don't think too hard about it because we're graphing things with different units on the same set of axes, right? So there's some kind of funny business going on there, isn't there? But these pictures are conceptually helpful, nonetheless. So if the acceleration is constant, that means that the velocity is, well, let's see here. Let's work this out. So suppose that your dv dt is equal to, let's say that this a is equal to minus g. dv dt equals to minus g. What happens when we integrate that? V is equal to, v naught minus gt. That's what we get from integrating that. So the velocity at time t would be some initial constant minus g times t. So here I'm assuming g is a constant, all right? What's the graph of v naught minus gt? Well, it's a line with negative slope, right? So it's something like this. So there's your velocity curve. What's the position look like? Well, position, right, v dy dt in this case, is equal to v, right, which is v naught minus gt. So if I integrate that, I get y is equal to y naught plus v naught t minus 1/2 gt squared, right? Integrating, putting in the initial conditions. So that is a parabola, right? And depending on the choice of initial conditions, I don't know where exactly it is, but it's something like that, right? And my bad. Is that the right way for the, this is a parabola with a negative coefficient of t squared. Is that what it looks like? That's a no dog, right? Oh, I'm sorry. Is the American Idol before your time? We all stopped watching. Did they bring it back? I feel like they brought it back. It was really good at the start when they made fun of people, and then they got all nice and stuff. It was boring. Those kind of shows are only as good as they're making fun of people. Just saying. Otherwise, you get the situation where they're just saying everybody can sing, which is like just not true. Sorry. We've all heard it. Anyway, so it should be a parabola which opens down, right? Any questions about the integration here? I went through it kind of fast. I mean, I can go through it more carefully. What I'm saying is that if you take the antiderivative of v, right, you get, let me break this down. Let me show you how I got that. So if we integrate, let's say from time 0 to time t of dv dt. Oh, goodness gracious, let me. Well, you guys didn't ask me to. Let me one moment here. Let me recalibrate this lecture here, over here. So, anyway, my point is, in one dimension, we have a relation between the velocity, the position, and the acceleration graph, right? Are we agreed? Okay. So, what would the meaning, and like there's also other things you can say, like if you look at the, the area under a specific, oh my bad. I gotta be careful here. So, if we integrate from t1 to t2, the velocity as a function of time, what's that give us? So the fundamental theorem of calculus, the net change theorem, if you like, that gives us x of t2 minus x of t1. What is that? That's the displacement, right? That's what I started talking about today. This is the displacement. But now it's one-dimensional, right? You said displacement was a vector. Yes, I still say it's a vector. But in one dimension, we have a convention. So it's simply this, that positive goes one way, negative goes another way. And that way it's a vector, all right? We can't get away with that in 2 or 3 dimensions, right? I mean, I can't tell you, like, you're in the positive direction of this room, right? That wouldn't make sense, right? We need a more interesting description for direction in 2 dimensions. But in 1 dimension, if you just define a plus, then there's a minus. If this is plus, this is minus, right? If we limit ourselves to just one-dimensional motion. So the integral, my point to you is just this. If we just have the velocity graph, which I'm trying to use my color code. What was it? Red, blue? I can't remember. Red. All right. Red is, so like here, if this is the velocity graph, right, then if I go from, say, time 1 to time 2, the area under this graph, right, is equal to the displacement in the question, right? All right. Okay, so let me just take a breath and derive some things here because they're kind of important. So if we have acceleration is constant, right, then we have v equals to, we have a sub 0 is equal to dv dt. And then we can integrate that, right? If you integrate this, it gives you the velocity at time t is equal to some, a naught times t plus some constant, right? Just taking the antiderivative. Then if I plug in time 0, what happens? V of time 0 is v of 0, oh my bad, is equal to a sub 0 times 0 plus c. So we see that the constant is v of 0. And then as a typical, I don't like writing v of 0 like that, so we just usually say c is equal to v sub 0, and that is my go-to notation for the initial velocity, all right? So wonderful. So the velocity at time t is simply the initial velocity plus the acceleration times time. This is the formula for velocity as a function of time, assuming what? We have to assume that the acceleration is constant, right? And then the question is, what kind of variable are you using? So we work, some problems will work with x, some problems will work with y. Let me show you the difference. So, typically, y, right? Aw, man. X. Aw, man, come on, you. It's disappointing. It's a little bit of, kind of bouncy. These ones hurt. I've been shot point blank by my 9-year-old. So, so let's just, in terms of letters, let me use an S here just to be generic, okay? Where did I put my marker? On the chair. Oh, thank you. So, great. But then S is arc length. So sometimes we use S as position. I'm sorry, it is physics. What can I tell you? So if this is equal to ds dt, then if you'll forgive me going through all the details, we integrate, and then we fit initial conditions to that. That gives us that the S at time t is equal to the initial position plus the initial velocity times time plus 1/2 a sub 0 t squared. So these are the constant acceleration formulas, right? So let's work some problems, yeah? For example, question, if, let's see here, if I throw this ball, right, oops, upwards, and it just barely hits the ceiling, how fast did I throw it? Do you understand the question? If I throw the ball from here, and it just almost hits the ceiling, how fast did the ball leave my hand? So that distance is 69.3 inches. So that's the problem we're going to work. Well, is example 2. So here's a picture. Give myself a top hat. So we're going up. The ball goes up. Make my big picture bigger. I regret the size of this picture already. So there's me. Ceiling. Oh, top hat, sorry. Bad. And so the ball is going up, and then it comes up here, and then comes back down, right? Then the question is V naught equals question mark. And I told you that this distance here is what? 69.3 inches. Instead of using that, let me use inch. So the first order of business is to convert that to meters. How many meters is that? 1.76. How do you know that?
Conversion on my paper.
Conversion on your paper? Oh, wait a minute. You have 69.3 inches converted on your paper?
Yeah.
That's random.
Yeah.
You must have a conversion factor, yes?
Yeah.
What is it?
1.76 meters.
1.76 meters is what?
69.3 inches.
Oh. All right. I see what. I'll talk to you more later, but not now. So 12 inches. Because we're talking past each other. So 1 foot is 12 inches, right? So we can multiply by 1. And if I want to convert feet to meters, I happen to know that 3.281 feet is 1 meter. So those are conversion factors that we can change units on, right? We just multiply by 1. And these things you have to look up somewhere or whatever. But 69.3 times, well, nothing, divided by parentheses 12 times, man, I hope I get what you told me, 3.281. But you're usually right, so I think I'm going to. What do you know, 1.76? I should just listen to you and just accept it. But then we're going to need you for the test, so that would be bad. 1.76, because it's generally discouraged to ask other students for help on the test. Yeah, we shouldn't do that. So 1.76 meters, apparently. So how do we figure out how fast the ball was leaving my hand? Yeah? Time? Time. Do we need to know the time? It seems like knowing time would have made things, that would be nice to have known the time, but we don't know. That's another interesting question. How long was the ball in the air? I'm pretty sure knowing how high it went is enough. Let's see how. Let's work it out. So what are the equations at play here? So the other thing I need to know, and I'm just kind of pulling this from the thin air, but there's gravity, right? And near the surface of the Earth, stuff drops at 9.8 meters per second squared, right? Although I'm always tempted for the purpose of the physics class to reset that to 10, just to make the calculations easier, but I'm not going to do it. Some year I'll rewrite all my physics notes and change Earth to Earthito or something. I don't know, something slightly different than Earth. So what we have is y. Let's write it down. Y is equal to what? Y is equal to the initial position, right? So let's agree that where my hand was, you can set y sub 0 to be wherever you want to be 0. All right. So for the purpose of this problem, it's convenient to say y equals to 0 is where I threw the ball from. So we're going to say that this is y sub 0 equals to 0. Just for the sake of making the formula easier. So we've got 0, and then we've got v0t. We don't know what that is. I mean, we don't know the v sub 0. We don't know the t yet. And then minus 1/2 gt squared. Right? Now, what else do we know? Velocity, right, in this case is v naught minus gt. Now we need to think about this. What can you tell me about the top of the flight? It's where the velocity was 0, right? So up here, we had velocity equal to 0. And we could say, let's call that t equals to t max. That's not the right word. I need to give it a name. T what? Ttop. Yeah, sure, why not? Ttop, I like that. So this gives us that 0 is equal to v sub 0 minus g Ttop, yeah? So what? Well, then what? So we know that Ttop is what? It's equal to, apparently, v sub 0 divided by what? G, right? Now you're like, but we don't know v sub 0. We're trying to find it. That's true, right? But what else do we know? And here I'm kind of not being, I'm just being a little bit more physical, but what can you tell me about the time to the top? Yep.
It's 1/2 the time back to the bottom.
1/2 the time back to the bottom, exactly. So that's useful because if we talk about y of twice the top time, what do we know about that? Yeah, but so I'm saying that the ball leaves my hand at y equal to 0, right? And it comes back at y equal to 0, right? So this is also 0. What else is it? It's the other displacement 0, that's true. But in terms of the kinematic formula right here, this is called kinematics, by the way, which is just fancy speak for study of motion. So v naught Ttop, right? Not Ttop, but what? Twice Ttop. Minus what? Minus 1/2 g Ttop squared. I'm starting to regret calling it Ttop, but I can't stop. Ttop, 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 Ttop. Now what? I've got two equations. I've got two unknowns, right? So you can solve them. How should we do it? So I think for this, what I'm going to do is I'm going to put, you know, Ttop equal to, so this gives me 0 is equal to v naught times 2 v naught over g, right? Minus 1/2 g, and what do we got? V naught over g squared. So I just substituted in for Ttop. I got rid of Ttop and replaced it with v naught over g, right? I substitute this equation into that equation. Now what do I have? Oh man, I've done something wrong here. Oh, I'm dumb. What was I supposed to put here? 2 Ttop. And what happens then? And this becomes what? True, but useless, right? So that was a bad move. See that? I mean, this is the same thing, subtracted the same things, equal to 0. Yay. What I should have done is gone back here and solved this equation, because this is a quadratic equation in t, which we can solve, right? So solve this instead. This is, you know, I'll factor the Ttop out. And we've got 2 v naught minus 1/2 g times 4 Ttop. I really regret calling that Ttop. But so there are two solutions, right? And they make sense. One of them makes sense immediately, right? Because when are you at y equals to 0? One of the times is at time 0, right, when the ball leaves my hand. So mathematically, that's got to be there, and it's there. T equals 0 is the solution. What's the other solution? Right here, right? So that's equal to 0, so that tells me what? Ttop is what? Two V naught, let's see here. Let me clean this up. It says 2 V naught minus 2G Ttop, which if I solve that for Ttop, I get, oh, the 2's cancel, right? So I just get what? V naught over G, yeah? And at this point, I regret my life. Well, not really, but there was an easier way to figure this out, wasn't there? Can you tell me? So there's the time to the top, which is not what we were after, but hey, we found it anyway. Now what's the initial speed? So V naught is equal to what? Oh man, I'm sorry. I've lost track of, just a minute. We haven't yet used the 1.76 meters, have we? Because that's going to have to be in play here. My point would be just a second here. So this is obvious because if you just use this equation right here, right? We could have just got it directly from here, yeah? 0 is equal to V naught minus G Ttop, right? So of course, that's the time to the top. That's the easier way to find it, right? So, what's next? We're trying to find the velocity, right? So what else do we know? Well, we know that 1.76 meters, right, is equal to what? It's equal to what? It's equal to V naught Ttop, yeah? Minus 1/2 G Ttop squared, yeah? Which is what? This is V naught times V naught over G minus 1/2 G times V naught over G squared, which is what? That's just V naught squared over 2G. By the way, that formula is useful for other problems. If you want to know how high something goes in terms of the initial velocity, that's the formula. Because when it leaves your hand like that to the top, oops, you know, V naught squared over 2G gives you the height from where it started. That's the formula for the height traveled there. Okay, so then we can find V naught. V naught's what? 2 times 9.8 meters per second squared times 1.76 meters square root. So the initial speed of the ball leaving my hand was what? So, you know, sorry I didn't show you the absolute fastest way to the solution here, but I don't think it's a waste of your time to see that this is a process, and this is how I work problems anyway. I write down the equations which are true for the physical problems. I think about what I have, think about what I'm trying to find, and I work through it. You know, eliminating piece by piece what I know from what I want. You know, what I'm trying to get where I want to from what I know, and if I need to do math along the way, I do, right? But sometimes, if you lose track of like common sense, you can make like a lot of trouble for yourself just doing math, right? Because if you see clearly the intuitive way of thinking about it, it's much faster, right? Like, this isn't even intuition. This is just like common sense. If I'm trying to find time to the top, I should look at velocity equal to 0. Use the velocity equation to find Ttop, right? Duh. So I'm too close to the board. I didn't see it. No, not a good excuse, but it's the excuse I'm giving you. 2 times 9.8 times 1.76 square root We like decimal numbers for answers in here. So I get 5.87, that's probably already too much, meters per second. How many miles per hour is that? What's that? 13.1? That sounds about right. I'll allow it. All right, so question. Oop. Try that again. So let's see here. I'm 177 inches from the wall, right? Can you guys time it for me? From the sound of my shooting to the sound it gets to the wall, how long is it? Are you ready? Anybody? How long was that? See, this is why in the lab you guys got like timers and stuff. It's helpful. Aw, man. See, this thing, you got to get it in the hopper. Let's try the back. Yeah, how far to the back of the room?
Like 0.7.
0.7 to the back of the room? All right, so I'll try not to shoot you in the eye. I should remember what we got last time. What are you doing? .607. Now, why is that motion easier? Why is that problem easier? It's not accelerating, right? So, what did I just say? It was 607 inches. And we shot the bullet at V0, back here. And we said that the change in time was 0.7 seconds. Is that right? Guesstimating. Okay, so what are the kinematic equations in this case? So I can say x equals to, x naught plus v naught t, yeah? What we know is that x minus x naught is 607 inches, right? If we're talking about the time to the back of the room, yeah? And what's the speed? I mean, the speed is constant, right? Because the acceleration in the x direction is 0, right? Yeah, the ball's dropping, although it looks almost horizontal, this thing, doesn't it? It's not bad. Anyway, so what's the speed here? Or I should say the velocity of the bullet leaving the gun. Can we figure it out? So here, V0, we can calculate from the change in x over the change in t. Now, why can I do that? When the acceleration is 0, the average velocity is equal to the instantaneous velocity, right? It's the velocity is constant, so I can get the velocity of the bullet by just taking the total change in position over the change in time, which in this case would be 607 inches divided by, well, we agreed 0.7 seconds. I don't know if that's actually reasonable or not, and that will give you a completely meaningless inches per second estimate of the speed of the bullets coming out of this gun, right? How can we convert that to something more interesting? Change inches to meters? Sure. All right, so my original plan for today was to get out the laptop and to like show you examples from lecture 3 and 4, right? I decided I thought it'd be more interesting if we actually worked problems out together, maybe. But I would point out, as you're looking at your homework, there are a slew of examples, if you look at lectures 3 and 4, that are constant acceleration. I hope this gets you started. I know we're not where we need to be yet, but anyway, if you have questions about homework, feel free to email me. I know we're out of time here in a moment. So.